So this will be problem number 2 from the 2022 AP Calc BC for your response set. This is a calculator question, and it tells us we've got a particle moving along the curve in the xy plane. Its position is governed by a set of parametric equations. So at time t, its x coordinates given by x of t, its y coordinates given by y of t, and time is only going to be positive. Particle moves in a way such that the rate of change of its x-coordinate is given by this function, and the rate of change of its y-coordinate is given by this function. They tell us that at time 4, the particle is at the point 1, 5. So in part A, we're asked to find the slope of the line tangent to the path of the particle at time 4. So the way that you're still needing to find the slope of the tangent line to a parametric curve is by determining dy dx, the rate of change of y with respect to x. Now the formula that you've developed and used to do that is to take dy dt evaluated at whatever the input is, in this case 4, and then to divide by dx dt evaluated at the same spot. In this case, calculator's in play, so you can just fire up the calculator, no special functions or anything needed. We just evaluate this at 4, evaluate this at 4, divide those answers, get 0.701 for that result. Part B asks us to find the speed of the particle at time 4. So the speed is going to be the magnitude of the velocity vector at time 4. The x component of velocity at time 4 is dx dt evaluated at time 4. The y component of velocity at time 4 is dy dt evaluated at time 4. To find the magnitude of the resulting vector, I just have to resolve that vector, and that simply amounts to applying a Pythagorean theorem with the x and the y components for velocity used as the legs of the triangle. So that's a formula that you're also likely familiar with, and if you evaluate this on the calculator, after plugging 4 in place of the t's in those bits of given information, you should end up with a speed of 5.035. You're also asked to find the acceleration vector of the particle at time 4. So we have access to the velocity component in the x direction and the velocity in the y direction. So if I want the acceleration components, I'm going to need to take the rate of change of the x component for the x component of velocity for the x component of acceleration, and I'm going to need to do the rate of change of the y component of velocity for the y component of acceleration. I need to evaluate those at 4. The calculator's in play here, so I didn't show any work in taking these derivatives or anything. I just used the numerical derivative option on the calculator to evaluate the derivative of dx dt at 4. I got 0.970 for that. Doing the same for dy dt, numerical derivative of that evaluated at 4 gets me 0.444. Part C wants us to find the y-coordinate of the particle's position at time 6. We're going to have to base that off of the y-coordinate that we know. So at time 4, we know the y-coordinate is 5, and I'm going to have to take that as my starting point and then add on, I should say starting y-coordinate rather than point. I'm going to take that as my starting y value and then add on how much the y value changes by integrating the rate of change of the y value across the time that I knew the y value to the time that I would like to know the y value. Again, the calculator's in play here, so you can just do that integral on the calculator. I included more accuracy than what the calculator provided with here. On the AP exam, you're always able to either round or truncate to the third digit past the decimal. Anytime at 5 with this fourth digit past the decimal, I usually just include it just to kind of be better safe than sorry. You're not penalized for including more than 3 digits of accuracy, but you are if you include less. In this case, 11.571 would be accepted as well. This isn't a case where we determined these, and these are obviously not irrational values, these limits of integration, but that's just kind of the habit that I'm in with regard to where I round or how I specify my result. And then the last part here asks us to find the total distance the particle travels along the curve from the time t equals 4 to t equals 6. So when you have motion happening along a line, to find the total distance traveled along that line, you do the integral of speed. Speed is the absolute value of velocity when motion is only happening in one dimension, either along the x-axis or along the y-axis. We use that same mentality here. To find the total distance traveled along a curve, this parametric curve, we are going to do the integral of speed. This is our speed formula from back in part B when we applied when we plugged 4 in place of the t's and did the calculation. In this case, we're not plugging anything in place of the t's. We're letting that speed formula become our integrand, and we have to do the integral of speed across the appropriate time frame, in this case 4 to 6. Calculator's in play here. Be careful with your input. A lot of grouping symbols need to be utilized here, and as long as you are, you should end up with a speed of 12.136. Not a speed, excuse me. You should end up with a total distance traveled of 12.136 across the time frame from t equals 4 to t equals 6. This is the same expression that you would evaluate for curve length, so for the length of a parametric curve. This is an application, so I just kind of talked about it in terms of the application prior to that, but this is literally just an application of the curve length formula as well, which is also a formula that you're likely familiar with.